In this video, we will analyze the running time, meaning finding the tightest bound of the following deterministic tape Turing machine that decides the language 0 to the m, 1 to the m, such that m is greater than or equal to 0, given a string w from the alphabet 0, 1, with the length of w being n. So we're calling the length of our input n, and our input may or may not be a string in this language. So it may or may not have m zeros followed by m ones for some value of m greater than or equal to 0. So let's look at the algorithm. So the Turing machine is m, and it takes an input string w, and what does it do? In stage 1, it's going to scan across the tape and reject if a 0 is found to the right of a 1. So stage 1 is making sure that our input is in proper format. Stage 2 is going to be iterative, so we're going to keep looping while there are both zeros and ones remaining on the tape. So if there are just ones remaining, then we would fall out of step 2. If there's just zeros remaining, we'd fall out of step 2. Or if there's nothing remaining, we would fall out of step 2. So within stage 2, I should say, there's 2 substages. So 2i is going to scan across the tape and check if the total number of zeros and ones, so the total number of zeros and ones remaining on the tape, is even or odd. If it is odd, we will reject. If it's even, we will continue. In 2ii, we scan across the tape and we cross off every other 0 and every other 1, starting from the first 0 and 1. Okay, and then we go back up to 2 and we check our condition, make sure there are still zeros and ones remaining on the tape. So once we have fallen out of step 2, because we no longer meet the condition, so we now have either no zeros remaining, no ones remaining, or neither zeros or ones remaining, we hit stage 3. If zeros remain when all ones have been crossed off, or ones remain when all zeros have been crossed off, we're going to reject. Otherwise, we accept. Okay, so the first thing that we want to do, really what we want to know is what's the running time. But first we should probably make sure that this actually decides the language 0 to the m, 1 to the m. Okay, so let's check to see how this algorithm runs and that it actually decides the language. So first thing, if we consider a string that shouldn't be in the language, something that looks like, I don't know, 0, 0, 0, 1, 1, 1, 0, right? This is not in the language. So when do we reject? We reject in stage 1. So we scan across the tape. So what we would be doing here is we would say, okay, check, I'm finding just zeros. Maybe we're not crossing them off. Maybe we're dotting them or just moving to the right, something like that. We don't say explicitly how to check, so I'm just going to cross them off for now. So we're going to say, I'm looking at zeros, I'm looking at zeros. Okay, now I've seen a 1. So I'm looking at ones, I'm looking at ones. There's a 0, right? And then we would reject that string. Okay, so that string gets immediately rejected in stage 1. So now let's see what happens in stage 2. So let's pick a string that should be accepted and see what happens, see how it works. Okay, so let's start with, let's do 5 zeros and 5 ones. How about that? Okay, so this string should be in the language. So we would pass stage 1, right? There's no zeros to the right of a 1. We get into stage 2. There are still zeros and ones remaining on the tape, so we go to 2i. We're going to scan across the tape and check if the total number of zeros and ones is even or odd. So we have 5 zeros, 5 ones, so the total is 10. It's even, so we continue. We're going to cross off every other 0 and every other 1, starting from the first 0 and 1. So we would cross off this one, skip the next one. This one, skip, this one. Now we'd start with the first one, this one, skip, this one, skip, this one. Okay? And now there are still both zeros and ones remaining, so we go to 2i again. We're going to check the total number of zeros and ones. We have 2 zeros, 2 ones, so 4 is even. We continue. Okay, so 2i. I cross off this 0, and then I skip the one that's left. That's no more zeros. Cross off this one, skip the one that's left. Okay, so it's 2i. We go back up to 2, check the condition. Both zeros and ones remain, so we go back into 2i. Okay, we check. There's 1 0 and 1 1, so 2 is even. We continue. 2i, we cross off this 0 and this 1. And now, when we go back to check the condition in 2, we're going to fail because there are no zeros and no ones remaining on the tape. Each one is crossed off. So stage 3, if zeros remain when all ones have been crossed off or vice versa, reject. Well, there's no remaining zeros and there's no remaining ones, so we would accept. So we accept this string. Okay, let's try one quickly that shouldn't be in the language, so let's do something like that. Okay, so we pass phase 1, stage 1. We've got 5 zeros and 3 ones, so 8, so we pass 2i. Now we're going to cross some things off. We go back up. We have 2 zeros and 1 1, so that's 3, and so we reject. Okay, so hopefully we have an idea of how this Turing machine runs. So let's see why this works. Okay, so we said again, stage 1 is going to check for the proper ordering. So if it's unordered, it's automatically caught by stage 1. So we know everything that gets into stage 2 is in the proper order. It's going to be all zeros followed by all ones. What we don't know is whether or not the number of zeros and the number of ones is equal. We need that to be in the language. What 2i is really doing is it's checking the agreement of the parity of zeros and ones. Okay, so for example, if we have, let's make a little, I guess a description here. So in 2i, if we have odd zeros and odd ones, okay, this means they agree. Okay, and it also means it's necessarily even, right? An odd plus an odd is even. If I have odd zeros, whoops. If I have odd zeros and even ones, they're going to disagree, and they're also going to produce an odd number. If I have even zeros and odd ones, they disagree, and they also give me an odd number, right? An even plus an odd is odd. And then if I have even zeros and even ones, they're going to agree, which also means they're giving me an even number. Okay, so stage 2 is checking that the number of zeros and ones remaining have the same parity. Okay, at each time after we've crossed off into II, after that when we come back up, what's remaining still agrees. Okay, now why does this help us decide if the number of zeros and ones is equal? So you can imagine that at one particular phase, for example, in our second string, when we started off, we had 5 zeros and 3 ones. They're not equal, but they have the same parity. Okay, so in that iteration, their parity agreed, but in the next one it didn't. In the next one we were left with 2 zeros and 1 1, so odd, so even and odd, right? And they didn't agree. So let's see why this matters. Okay, so what stage 2 II is doing is it's cutting the number of zeros and ones in half and throwing away the remainder. Okay, and maybe you've seen this before. This is basically computing the binary representation of the number. So let's do a couple examples just to see that this is actually true. So let me start with the number 10. Okay, so 10 is even, so I'm going to put a 0 here. Now I'm going to do 10 divided by 2, which is 5, so I have a 1. 5 divided by 2, throw away the remainder, is going to give me 2 left, which is even. and then 2 divided by 2 is 1, which gives me 1. Now if I read this backwards, in reverse, I have the binary representation of 10. So let's do 11. So 11 is odd, gives me a 1. 11 divided by 2 is 5. That's odd. 5 divided by 2 is 2. It's even. 2 divided by 2 is 1. That's odd. Read it backwards. 1, 0, 1, 1. This is 11. Let's do 12. So it's even. 6 is even. 3 is odd. 3 divided by 2, throw away the remainder, is 1, is odd. So I have 1, 1, 0, 0, which is 12. Let's do one more. I'll have to put it over here. 13 is odd. 13 divided by 2 is 6. That's even. Divided by 2 is 3. That's odd. Divided by 2 is 1. That's odd. 1, 1, 0, 1 is 13. Okay, so what does this have to do with it? At each step, as we cut the number of zeros, let's just focus on the zeros for a second. So if I start out with 10 zeros, at the beginning I'm even, so I have a 0. After I've done one stage 2 II, where I'm crossing off some zeros, I'm left with 5 on the tape, and so I'm going to have a parity of 1. Okay, after I cross off again, I have 2 remaining, so I have a 0, or an even. Okay, so you can see that the parity at each iteration is going to reflect the binary representation of the original number left, starting on the tape, excuse me. So, bringing it back to what we're doing in 2II, where we're checking to see if the parities agree, right? We just said this here. We're checking for agreement. We're checking for agreement after every iteration of 2II. Okay, so since this is basically the same thing as computing the binary representation, the only way for them to agree all the time for every iteration is if they're the same number. Okay, otherwise at some iteration they're going to disagree. So for example, let's take two numbers that are very similar, 12 and 13. So in this case, right off the bat, they would disagree. They would disagree in this bit. Okay, or you can think of it as when they're checked for agreement, they're going to disagree. Okay, let's take another number that might, here we go. Let's take, if we consider, let's say that there are 11 zeros on the tape. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 ones. Okay? These seem very different, but you'll see in a minute why I picked these. So, at the beginning of the computation, if these are my zeros and these are my ones, I have 11 of these and 3 of these. Okay? 1 is odd, gives me a binary 1. 3 is odd, gives me a binary 1. Okay? We can also see that 14 plus 3 is even, so we would go ahead and continue. Okay, now we cut, or cross off, cut in half. Okay, now what I have left for zeros, 1, 2, 3, 4, 5, which is odd, gives me a 1. And for 3, I have 1, which is 1. 5 plus 1 is 6. We're still even. We continue. Now when we would cross off, okay, in this case, I would have 1, 2, 2 zeros remaining, which is even. But now I have nothing left to do with my ones. Okay, so even though these two binary numbers started out the same, because what's 11? 11 is 1, 0, 1, 1, and 3 is 1, 1. And remember, we're working from right to left. We're creating this number backwards. Okay, so these are going to start off being the same, but at some point they're going to differ because they had a different number on the tape to begin with. They have a different binary representation. In this case, actually, rather than finding out by the disagreement, I showed you another example. I think 12 and 13 will disagree right away. If we had picked a number like, I don't know, 5 and 13 would agree for a while, okay? But instead, for the case of 11 and 3, what's going to happen is instead of checking for agreement, on that last step, I kicked off the very last one, but I had some zeros remaining afterwards. So what does that put me in? That says when we go back up to 2, we no longer have both zeros and ones remaining. So we drop down to 3. And in this case, zeros remain when all ones have been crossed off. So we reject. Okay? So, just to recap what's happening. 1 gives us proper ordering. Okay, we reject if we don't have proper ordering. 2, we're going to reject if at some point the parities disagree because the binary representations are not the same. We differ in some bit. Okay? In phase 3, if we enter phase 3, either no zeros and ones remain, okay, at which point we accept. Why do we accept? Because we agreed on every parity check. We passed every parity check, and we eliminated all of the zeros and ones in the same number of steps. So that means the number of zeros and ones at the beginning was equal. So we go ahead and accept. Otherwise, even if we've been agreeing for a while, like in the case of 11 and 3, we've passed all of our parity checks, but we get into phase 3, or stage 3, and now we have some zeros left after we've crossed off all the ones, right? This is because the number of zeros was larger than the number of ones, like 11 and 3, and so we can no longer match zeros to ones. Okay, so these numbers are not equal, so we're going to reject. Okay? So hopefully it's clear that this Turing machine actually does decide the language. So let's check the running time. Okay, how long does stage 1 has to check the entire length of the input. Okay, so that's done in big O n time. Okay, it takes about n steps to check across the entire tape. In reality, if there is a 0 to the right of a 1, let's say we have something that looks like, okay, we're going to reject as soon as we see this 0. But we're not looking at best case analysis or average case analysis, we're looking at the worst case. And in the worst case, something that looks like this, right, we have to check the entire length of the input to find out that there's a blank after the 1. There's no 0. Okay, so we say that one runs in big O n. Okay, let's check stage 2i. Okay, it again has to check the entire length of the tape. It has to check all of the input. So big O n. Stage 2ii has to go across the entire tape, right? So big O n. 3. How do we check this? We need to check the entire tape. We need to check to see if there are any zeros that haven't been crossed off or any ones that haven't been crossed off yet. Okay, and if we find any, we reject. Otherwise, we have to get all the way to the end and see that every one has been crossed off, and then we can accept, assuming all of the zeros have been crossed off as well. So in stage 3, it's big O n. Okay, so each stage takes big O n. However, 2 is iterative. Okay, so we want to know how many times do we have to execute stage 2? Okay, well, if we think about it, stage 2ii is going to cross off at least half of the zeros and ones every time it's executed. When does it stop? When all of the zeros or all of the ones both are eliminated. Okay, so in the worst case, it stops when both are eliminated. Okay, we have to eliminate all of them when they're equal. Okay, so how many iterations does it take? It takes 1 plus log base 2 of n. Okay, and in big O notation, This is big O, and I'm going to leave the constant in for a minute, or the base in for a minute. Okay? So this is how many times we execute stage 2, stage 2 in total. Okay, so let's write this down. So what does this mean for our running time? We have running time big O n plus, oops, okay, we have big O log base 2 of n times big O n plus big O n. Why is it plus? Because 2i and 2ii are sequential. Okay, first I is executed and then II is executed. So it's additive. Okay, and then we have stage 3, which was big O n. Okay, and now if we want to collect like terms, we have 2 big O n plus big O log base 2 of n times 2 big O n. Okay. Now let's drop the constants. So we have big O n plus big O log n times big O n. Okay, and we know this is the same thing as big O n plus big O, oh, I should put the n on the other side just for clarity. Okay, big O n log n. Okay, and then when we take the leading term, because that's all we care about, we end up with running time big O n log n. Okay, so that's the running time for this Turing machine M.